or false, the eigenspace always contains the zero vector. True. In fact, any vector space always contains the zero vector. Whether I name it the eigenspace or the null space or the subspace of R4 that's spanned by these vectors, any vector space always contains the zero vector. That's one of the pieces of the definition of a vector space. Okay, so the eigenvalues of a triangular matrix are the entries in the first row of the matrix. False. What are the eigenvalues of a triangular matrix? They're the entries on the main diagonal. Yep. All right, true or false, an eigenvector must be non-zero. True. And then the eigenspace is made up of the eigenvectors plus the zero vector. Okay, so today we're going to define an eigenvector and an eigenvalue. I'm going to do a small thing to try to show you how it's going to apply, but we don't really have enough theory to fully apply it yet, but I'll try to give you a little preview so that you're not like, what is this? Okay, so from the reading, an eigenvector of an n by n matrix, A, is a non-zero vector, right? So it has to be non-zero. Non-zero vector x such that ax equals lambda x, okay, for some scalar lambda. And lambda is called an eigenvalue of A if there is a non-trivial solution, a non-zero solution to ax equals lambda x. And x is called the eigenvector corresponding to lambda. So last class we solved finding steady state vectors and we solved ax equals x. This is a generalization of this, right? This is a generalization where lambda is 1. Today we're doing a generalization. Finding the steady state vector was a specific example of finding the eigenvector corresponding to a eigenvalue of 1. So the equation ax equals lambda x is equivalent to the equation a minus lambda I x equals 0, right? So I did a similar thing when we were solving for steady state vectors, except I just did a minus I, right? Because lambda was 1. The set of all solutions to a minus lambda I x equals 0, that is the null space of the matrix a minus lambda I, right? That's the set of all vectors x that get sent to 0 for the matrix a minus lambda I. And we often call this subspace of Rn the eigenspace of the matrix A. Okay. The set of all eigenvectors plus the zero vector make up the eigenspace. The eigenvalues of a triangular matrix are the entries on its main diagonal, and we'll see an example in the group activities to help justify that. 0 is an eigenvalue of A if and only if A is not invertible. And we'll see an example in the group activities to help justify that also. If you have a set of eigenvectors that corresponds to some distinct eigenvalues, then the set V1 to VR, the set of eigenvectors, is linearly independent. Okay, so if you come up with a set of eigenvectors, each one corresponding to a different lambda, they are automatically linearly independent. Yes, Todd. I is the identity matrix. Yeah. We'll see an example in the group activities to help justify this linear independence thing of the eigenvectors corresponding to different eigenvalues. And then you can use lambda and its corresponding eigenvector x naught, we'll call it, to find solutions to first order difference equations like the ones we discussed in 1.10 and 4.9. Those sort of recursive difference equations where x sub k plus 1 equals a times x sub k. So we did some of these last class. So you can build solutions to these kind of equations using an eigenvector and an eigenvalue, right? So you could solve this by saying x sub k is equal to lambda to the k times x naught, the eigenvalue to the k times the eigenvector associated with lambda. And then you can just take k to be any value. So if I wanted to know the solution after 10 years, to say that like Democrat, Republican, Libertarian problem you did last class, instead of solving for the steady state, which is what happens way in the future, and instead of doing the iteration 10 times, you could just use this and plug in k equals 10, right? So you could just, it's a way of finding a solution explicitly rather than recursively. And then if you take linear combinations of those solutions, those are also solutions. And this is really important in an ODE class, right? We will expand upon this a lot next semester if you take differential equations, how to find solutions to these kinds of equations. And we'll do a little bit more with it next class. Ordinary differential equations. Yeah, ordinary is in opposition to partial, right? So partial differential equations is kind of like Calc 3 to Calc 1, PDE is to ODE. Yeah. Sorry. When it's the only thing you've ever seen, you can just call it differential equations. Yeah. Okay, so I just want to do a brief explanation of why this thing represents an explicit solution to this recursive equation that we have. Okay. So if I have a times x to the k, right, I'm claiming that lambda to the k x naught is a solution to the equation ax to the k equals x to the k plus 1, x sub k plus 1. So I'm just going to write out the original equation. It says x to the k plus 1 equals a x to the k. And I'm going to claim that x sub k equals lambda to the k x naught is a solution, right? So that means if I plug this in for x sub k in the equation, I'm supposed to just get a true statement, right? That's what it means to be a solution. So I'm going to come over here, and I have x sub k plus 1 equals a, and I'm going to replace x sub k with my proposed solution, lambda to the k x naught. Sure. Yep. Okay, so I'm trying to show that these two are the same. So I can switch the order here. X to the k is just a scalar, so you can put scalars wherever you want. So this is lambda to the k times a x naught. Now, because lambda is an eigenvalue, right? Lambda is an eigenvalue of a. So this is a side note over here. Right? The definition of an eigenvalue is that ax equals lambda x, right? That's the definition of an eigenvalue. So a times x naught, I could replace with lambda times x naught because lambda is an eigenvalue. So I've got x sub k plus 1. Does that equal to lambda to the k times lambda x naught? And then what is lambda to the k times lambda? Lambda to the k plus 1 x naught. Yep. I'll come back to it and justify it better, but this is the definition. If lambda to the k, if x sub k is lambda to the k x naught, then x sub k plus 1 has to be lambda to the k plus 1 x naught. So I think that's why. Yeah. Okay, so on to some more concrete examples. Is 1, 3 an eigenvector of A? So we should multiply A, 1, 6, -1, -4, by 1, 3, right? And what I'm getting, if it's an eigenvector, I should get a multiple of 1, 3 as a result, right? So when I do this multiplication, I get -2, -6, right? And -2, -6 is a multiple of 1, 3, right? I could rewrite that as -2 times 1, 3. So my answer is yes, right? It is an eigenvector. And what is the corresponding eigenvalue? -2. Right? It's the scalar multiple is the eigenvalue. So this is the A x equals lambda x. Okay. So we've satisfied the definition of an eigenvector. Is that okay? All right. Consider the matrix 3, 2, 0, 1. Is lambda equals 3 an eigenvalue? So this is a little bit different. Instead of giving you a possible eigenvector, I'm giving you a possible eigenvalue. So we have to find out, is there a non-zero solution to ax equals 3x, right? Put in a 3 for lambda, which is the same thing as saying ax minus 3x equals 0, which is the same thing as saying a minus 3I times x equals 0. Right, because if I distributed this x, I'd get ax minus 3x. All right, so how would I solve this equation? Yeah, I would subtract, I need to get a matrix for a minus 3I, right? So let's do that. A minus 3I. A is 3, 2, 0, 1. And 3 times the 2 by 2 identity is 3, 0, 0, 3, right? Because the identity is 1, 0, 0, 1, and I multiplied the whole thing by 3. So then when I subtract, I get 0, 0, 2, -2. So I'm really trying to solve the equation 0, 0, 2, -2 times x1, x2 equals 0, 0. It's a 0 vector. So how do I solve that matrix equation? Augment the a minus 3I with zeros, row reduce. Okay. So I actually already did it. So I have 0, 0, 2, -2, augment with 0, 0. And that is equivalent to 1, 0, -1, 0, 0, 0. Okay, does this have a non-trivial solution? It has infinite solutions, yeah, because there's a free variable, so there's going to have infinite solutions. My basic variable is x1, and so I'm going to write that in terms of my free variable x2. Right. So any vector that looks like x1 x equals x2, where your two entries are equal, is going to be an associated eigenvector, right? So this is true. Yes, it's an eigenvalue because there is a non-trivial solution. There is a vector other than 0, 0 that will make this equation true. Right? So actually any multiple of the vector 1, 1. Right? This is all the solutions. Yeah, so 1, 1 is your basis, right? Because the span of 1, 1 generates every solution. Infinite number of eigenvectors associated with lambda equals 3. They are all of the form some scalar times the vector 1, 1. So one eigenvector associated with lambda equals 3 would be 1, 1, or 2, 2, or 3, 3. So there's an entire infinite number of eigenvectors associated with lambda equals 3, and we call the set of all of those eigenvectors the eigenspace. Okay. So the eigenspace is the set of all vectors, all eigenvectors, plus the 0 vector. So its basis would be 1, 1, because we can take linear combinations of 1, 1, which just means scalar multiples of 1, 1, and we get another vector in the eigenspace. And this will also include 0, 0, because we could take the scalar to be 0. So 3 is an eigenvalue. Yeah, I should have written yes somewhere, right? Yes. Because there is a non-trivial solution. There is a solution other than this vector 0, 0 that makes this equation true.